Math 2414, Trigonometric Substitutions, Video 9, another example using secant. Second to last video in this series, the last one will just summarize everything. Let's take a look at this one. The integral of the square root of 2, the integral from the square root of 2 to 2 of 1 over t cubed times the square root of t squared minus 1 dt. I am very tempted to change this. I'm afraid that if I do, though, I'm going to throw it to an unintentional tailspin. So I'm not going to change it. The thing I was worried about is I'd like for this one to be a number that's different, so I'm going to make a leap of faith here. I hope I don't regret this. I'm trying to see through to the end of the problem to anticipate. I know there would be a problem if I put a 4 here, because if I put that square root of 2 there, then I would get a negative number under the square root. So I am going to leave the 4 there, but I'm going to change the limits of integration. The problem will still essentially work the same. I just can't promise you how pretty it'll come out to the end. Let's see if I can pick some good limits of integration. Let's try the square root of 5. I can get it to draw. And let's take it from the square root of 5 to, we'll say 4. And we already got 4 there. Let's do 6. Yeah. All right, I'm not sure how the answer is going to look, but truth is, don't care. Because for those of you who are going down the theoretical path, the specific problem is not as important as the general problem. And for those of you going down the applied path, the math is rarely ever pretty. So don't be afraid that things are going to go crazy. I know how this problem is going to go, but since I change it, let's see what happens. All right, so we're going to do a substitution based on the fact that we're trying to collapse the t squared minus 4 down to a single term. And again, the trig identity that we're trying to capitalize on, secant squared theta minus 1. In fact, let's go ahead and write the tangent squared theta over here. Should have been doing this all along. We're trying to line up our subtraction problem with this subtraction problem. But the problem is the 4 and the 1 don't match, and that's easy to fix by multiplying the bottom equation by 4 on both sides. So 4 secant squared theta minus 4 is equal to 4 tangent theta. Now that we got the minus 4s lined up in the subtraction problems, we only have to compare our variable terms. T squared is equal to 4 secant squared theta. And if we solve for t by square rooting, get t equals 2 secant of theta. So that's going to be our substitution. Let's clean it up. All right, if we let t equal 2 secant theta, then we need to differentiate. And dt is equal to 2 derivative of secant theta tangent theta. Oh, and by the way, one thing I meant to mention earlier, the choice of theta, Greek letter theta as a variable, is actually completely irrelevant. I can use any variable I want. Since x isn't being used in this problem, I could have said secant x. It's just customary, at least for me, to use Greek letters for angles, and theta being a very popular such Greek letter. But we're not done with the substitution because we also have to draw the picture of it. So if we draw a right triangle, stick a theta in there, and solve for secant theta up there, we have secant theta equal to t over 2. Since secant is a reciprocal of cosine, and cosine is adjacent over hypotenuse, and secant is hypotenuse over adjacent. And if you're wondering why I say that every time, because that's how I remember the definition of secant. I can memorize it as hypotenuse over adjacent, but I know it's reciprocal of cosine, and I know the definition of cosine. So secant is hypotenuse over adjacent, so we need the hypotenuse to be t, we need the adjacent to be 2. Then we did the Pythagorean theorem. Then we get the opposite side to be the square root of t squared minus 4. Again, not a coincidence, it's the same square root in the radical. Now, this is a definite integral, so at some point we're going to have to put the 6 and the square root of 5 back in for t. But for now, I'm going to abandon the limits of integration. Well, I can't bring myself to do it. I'm going to leave them, but I'm going to put reminders on them that they're both values of t. And this actually is not that uncommon when you're doing substitutions. The reminder that this isn't the value of the variable we're integrating with respect to. All right, let's plug everything in. I get the feeling we're going to need a bigger radicand. t is 2 secant theta, so t cubed would be 2 cubed, which is 8 secant cubed. And let's be expeditious with dealing with the square root, because we know what's going to happen in the square root. Oh shoot, I erased it. It was on the previous screen. So let's just do it underneath here. When I put in 2 secant theta for t, I'm going to get 4 secant squared theta minus 4. But that was equal to 4 tangent squared theta. And it's getting square rooted. So the square root of 4 tangent squared is 2 tangent. And then our dt was 2 secant theta tangent theta, running out of room here, d theta. Very good. All right, so let's see how this mess is going to clean up. In the top of the fraction, bottom of the fraction, we have a tangent, so that's good. The 2's will cancel. Remember, you can cancel parts of multiplication problems and fractions. And even one of the secants is going to cancel. That will leave a secant squared down there. Let's see where we are. We have the integral from t equals the square root of 5, 6. Oh, by the way, if you're wondering why did I not change the limits of integration, because I would have to put t equals the square root of 5 into our substitution right here and solve for theta. I don't really want to do that, because I think dragging around a secant inverse of square root of 5 over 2 is just not worth it. All right, so what are we left with? We're left with d theta, clearly. Most everything disappeared. We're left with the 1 on top and 8 on the bottom and a secant squared on the bottom. Wait a minute, secant squared on the bottom? That would just reciprocate, become a cosine squared. These problems will drag out forever if you let them. So it's kind of important that you look for spots to streamline the process. Now, don't get me wrong. If you want to write every single step because you feel like you need to, that's what you do. But at some point, especially you future physicists and engineers and theoretical mathematicians, at some point in the future, you're expected to do things like I just did and clean up this integral real fast. All right, we got the integral of cosine squared, and we know how that game goes. When we integrate cosine squared, we use a power-reducing formula. We have 1/8 times 1/2 plus 1/2 cosine 2 theta. Now there is a disadvantage to using the power-reducing formula. It changes the argument of the trig function to 2 theta, but our triangle is a triangle about theta. So at the end, we have to use a double angle formula to change the 2 theta back to a theta. Let's move this integral to the next page and proceed. Continuing, we could probably pull out the 1/8, and while we're factoring things out, why don't we factor a 1/2 out of the addition problem, multiply it times the 1/8 to make it a 1/16. Just drop it in front. And now we're here. By the way, if you don't write t equals, it is not a catastrophe. It's just a constant reminder that those are 2 values. Now we're just going to integrate 1 plus cosine of 2 theta. And I probably could have thought that and integrated it, but I felt like it was worth writing before integrating. Integral with respect to theta of 1 is just theta. And for cosine, the integral of cosine of sine, technically we would do a u substitution. But if we did, it would be u equals 2 theta. And I've said this before, and I'll say it again and again. If you're going to do a u substitution, but the derivative is a constant, don't bother. Just integrate. And remember, you have to balance with the reciprocal of the derivative of that substitution. If u is 2 theta, du would be 2 d theta. And so I'll have to balance with the 1/2. And if you're ever not sure, just check the derivative. The derivative of that would be 1/2 times cosine 2 theta times 2, is the chain rule. 2 and the 1/2 would cancel. That's constant. All right. Remember when I said we're going to get a 2 theta and we didn't want it because our triangle doesn't involve it? Then we're going to need to use a double angle formula to get rid of that 2 theta. So what is that double angle formula? And yeah, I paused the video and drew the triangle on the second page. That double angle formula, write everything else. Sine of 2 theta is 2 sine theta cosine theta. Wait a minute. I don't need a plus c. The definite integral. Definite integral going from t equals the square root of 5. And, you know, in all practicality, we could have lost the limits of integration from the beginning, done the indefinite integral, and then at the end, evaluate the definite integral. But I've already brought us this one. All right, the 1 and the 2 half cancel, the 1 and the 2 halves. The half and the 2 cancel. So that's good. But what about the theta and the sine theta and the cosine theta? Well, theta, what was our substitution? Our substitution was t equals 2 secant theta, I believe. Yeah, that's the substitution I would use there. And so if we solve that for theta by dividing by 2 and doing arc secant, we would get that theta equal to arc secant of t over 2. And if you're wondering how come sometimes I solve for theta and sometimes I don't, it all depends upon if the theta exists in your answer outside of a trig function. If it exists inside of a trig function, then your triangle tells you what to do. But if it exists outside of the trig function, like that theta, then you actually need to solve for theta by using an inverse trig function. All right, so our theta is arc secant of t over 2 plus, in our picture, sine of theta is opposite over hypotenuse, and cotangent theta is adjacent over hypotenuse. So sine of theta is square root of t squared minus 4 over t, and cosine of theta is 2 over t. And at this point, I can drop the t equals because I have the correct limits, the correct variable inside of it. All right, we're almost there. Let's move this to the next page and figure out how far we can push this algebraically. And the answer is going to be not too far. I brought the problem over, but I did make a couple of minor cleanups after the plus sign. Number one, I took this multiplication problem in the numerator, put the 2 in front because it looks better there. And number 2 in the denominator, I just multiplied the t to make them t squares. Other than that, it's the same. All right, let's evaluate this and see how much we can clean it up. I'm not suspecting much. We're going to get one of those kinds of answers. All right, let's start by putting in the 6. If we put in the 6 inside the arc secant, we get 6 over 2, which is 3. And without a calculator, that's as far as you would push that. Plus, if we put a 6 in the other half of the addition problem, we get 2 on top. Well, that's already there. On the bottom, 6 squared is 36. And under the square root, we get 6 squared minus 4. That's 36 minus 4, which is 32. It's going to merit some cleanup, not just the reducing the fraction, but simplifying the square root. We'll get to that in a minute. Minus 1/16, and maybe I shouldn't have spread this out so much. I'm going to pause this and be a little bit more frugal with my space. All right, that's a little bit better. Now minus what we get when we substitute the square root of 5. So 1/16, giant parentheses, arc secant of t over 2, so the square root of 5 over 2, nothing going to happen there. Yeah, too early with that. Plus 2. On the bottom, we square the square root of 5 to get 5. And on the top, we get the square root of the square root of 5 squared minus 4. The square root of 5 squared is 5. 5 minus 4 is 1. Square root of 1 is 1. So we get 2 times 1. I did choose the square root of 5 because I knew it would play nice in there. Maybe I should have chosen another better number for the numerator. Excuse me, for the 6. But that's okay. All right, so is there anything we can do here? Yeah, I mean, just some algebraic cleanup. I'm tempted to distribute the 1/16, but yeah, I don't know if there's going to be any benefit because of these 4 terms are no like terms. You got 2 arc secants with different arguments. We can't put them together. And the other parts, one has a square root, one doesn't, so we can't put those together. So I really don't see a benefit to distributing the square root of 1/16. but I could factor it out. Have one of them. All right, so we're going to factor out the 1/16 out of both halves of these fraction problem. All right, so we got arc secant square root of 3. The square root of 32 will simplify into 4 square root of 2. And we can reduce the 4 with the 36 to get a 9. So it looks like that fraction's best cleanup is going to be plus 2 square root of 2 over 9. Minus, remember we factored out the 1/16, so we're going to have to write that. But we do need to distribute the negative sign. So minus arc secant of square root of 5 over 2. Minus 2/5. And as ugly as it is, I think it's a good stopping point for this problem. You may recall that I made some changes at the beginning. I changed the t squared minus 1 to t squared minus 4. I changed the limits of integration. I'm not going to redo the whole problem, but I'll summarize quickly what would have happened and why it was actually set up that nicely. In fact, that problem is number 43 from the 6.2 homework in the Stewart book that we're using. If it had been t squared minus 1, then the arc secant would have been arc secant of t, not t over 2. And when we substituted, we would have had arc secant of 2 and arc secant of square root of 2, which actually have nice values because arc secant of 2 is the same as arc cosine of 1/2, and arc cosine of 1/2 is pi over 3. And if we had arc secant of the square root of 2, that's the same as arc cosecant of 1 over the square root of 2, square root of 2 over 2, and that's pi over 4. So yeah, I changed the problem, which really didn't change anything except how the answer cleaned up. So just a heads up for those of you who are in my class, I am going to assign a question in the homework that looks a lot like this one. In fact, it will be the one that I started with, but it'll have a nicer cleanup. And if you were listening closely, I kind of told you what you know